So this is our project on muscle contraction and the sliding filament theory by Henry Burns and Justin Alpers. Um, so muscle contractions, the process starts when a signal is sent from the brain to a somatic neuron, and at the axon terminal, there are vesicles in the somatic neuron containing acetylcholine, and this acetylcholine is then released into the neuromuscular junction and binds onto receptors, which then causes the sodium to also bind to receptors because there's a sodium-potassium pump on the sarcolemma. When the sodium binds to receptors, this causes an action potential down sarcolemma and into the T-tubule. Once the action potential has come into the T-tubule, there is calcium in the sarcoplasmic reticulum which surrounds the T-tubules, and the calcium channels open up and calcium is released from the sarcoplasmic reticulum.
So now we're on to the part of the muscle contraction where the calcium is now left the sarcoplasmic reticulum due to the action potential moving through the T-tubule. So now at this time, the calcium will now move to the actin and the myosin. So now once the calcium gets to the actin and the myosin, it binds to the troponin on the actin, because on the actin there is tropomyosin, and the myosin cannot bind to the actin while the tropomyosin is still present on the actin. So once the calcium binds to the troponin controls where the tropomyosin is, and once it binds, it shifts the tropomyosin out of the way so the myosin can actually bond. But before the myosin bonds, it needs to be moved from the low energy configuration to high energy configuration. So for this to happen, ATP needs to bind to it, which then causes the myosin heads to move from low energy configuration to high energy configuration. At this time, now the myosin can bond to the actin, and then it binds to the actin binding sites, which forms cross bridges. So now at this time, the ADP is transformed into ADP plus PI plus energy, and then the myosin goes back to a low energy configuration, which pulls the actin towards the other actin. At this time, the actin nor the myosin, they don't get any shorter, so they just come closer together, because at the beginning they're separated, and then once the myosin pulls, they just come closer together, but they neither get shorter during this time. So then for the muscle to actually relax, since it would still be bound, the ATP needs to rebind to the myosin, which breaks the cross bridges formed and then allows the actin to release from the myosin and then reset to normal.
So then how this process is different during rigor mortis, all these first steps are the exact same, except when we get to the actin and myosin. Rigor mortis occurs after a person has died, usually 24 to 48 hours. And since the body is dead, it's not producing ATP anymore, so the body does still have enough ATP to bind to the myosin to move the heads into the high energy configuration, and then it's transformed, or it's hydrolyzed into ADP and PI, and it moves, tracks into the low energy configuration, but then there's no ATP left in the body. And this causes the muscles to not be able to relax. And so they are stiff and contracted, and they're not able to open up.